In dealing with proof, there are 4 terms you will come across. A mathematical proof is a list of statements in which every statement is one of the following. Firstly, an axiom. Secondly, derived from previous statement. And lastly, a previously derived theorem. Okay, next we continue with hierarchy of terminology. First, we have a proposition. Proposition is true statement of interest that you are trying to prove. Secondly, theorem. Proposition that are considered to be extremely important. Thirdly, we have lemma. Lemma is preliminary proposition that is used in a proof of the theorem. Lastly, we have a corollary. Corollary is a true statement that is a simple deduction of a theorem or proposition.
Next, for the construction method, based on the statement, if such and such, then there exists an object with a certain property such that something happened. We can conclude that the A, which is the hypothesis, is such and such, and B, which is the conclusion, is there exists an object with a certain property such that something happened. In general, the construction method is a technique for dealing with some statement in the backward process that contain the quantifier there is or there are or that exists. There are no fixed rules for constructing an object. Sometimes it is by trial and error or by an algorithm that can be designed to produce the desired object. It depends on the particular problem. Next, for the general outline. Basically, the guideline of the construction method similar to forward-backward method, which is number 1, recognize the statement if A then B has a potential quantifier there is or there are in B. Second, use the backward method repeatedly until the key question can be asked or can be answered. Number 3, write BI, which is I equals to 1, 2, 3, and so on. The answer of the key question using definition or previous knowledge. Number 4, identify object in backward process. Number 5, construct the object by using information from A. Number 6, which is the last step, is use the forward method, write A1, A2, and so on until the last statement derived from B is obtained.
So let's look at the first example. If n is an integer and n is an odd integer, then n squared plus 3 is divisible by 2. So, solution for analysis of proof. A, we get from the hypothesis. N is an integer and n is an odd integer. B, from the conclusion, n squared plus 3 is divisible by 2. Then we write P1 to show that there is an integer k such that 2k equal to n squared plus 3. Then we write A1 from A, which is hypothesis. Let n equal to 2a plus 1. Then A2, we substitute A1. N squared plus 3 equal to 2a plus 1 power of 2 plus 3 equal to 2a squared plus 4a plus 4. Then we factorize equal to 2a squared plus 2a plus 2. Then we write A3, we simplify A2, so which is n squared plus 3 equal to 2k, whereas k equal to a squared plus 2a plus 2. So we get A3 equal to B1.
Next, example 2. If x is even, then x squared is even. A. X is even because we get it from the hypothesis. B is x squared is even from the conclusion. B1. There is an integer k such that x squared equal to 2k. That is what we want to be sure. A1 x equal to 2k for some integer r a2. Therefore, x square equal to in bracket 2r square equal to 4r square equal to 2 in bracket 2r square equal to 2k, where is k equal to 2r square. So, a2 equal to b1.
Okay, lastly, for the example of 3, which is the question is, if the function fx is equals to square root x plus 1 is continuous in the interval 0, 3, then there exists a value c that satisfies the mean value theorem for integral. Okay, lastly, for the solution is, with the analysis of proof, which is for the hypothesis, we know that the hypothesis is fx equals to square root of x plus 1 is continuous on 0, 3, while the conclusion is there exists a value c that satisfies the mean value theorem for integral. For B1 is what we want to show. So we want to show there is a value c in 0, 3. So how we gonna to do it? So basically, from A1, we can use the mean value theorem formula, which is integral BA fx dx equals to AC times with B minus A. So for A2, we use the integral 30 function fx, which is square root of x plus 1 dx equals to fc, which is we substitute the c value to the x value, which is square root c plus 1 times with 3b, which is 3, and a, which is 0, so 3 minus 0. So for the next step is we integrate the square root x plus 1. It will be square root x plus 1 times cube, x plus 1 cube divided by 3 over 2 equals to square root c plus 1 times with 3, which is 3 minus 0 is 3. So for the next step, for the 3 over 2 we can take the 2, we can times the 2 with square root x plus 1 cube over 3. So it will be like that, equals to 3 square root c plus 1. So after that, we substitute the value of 3 and 0 equals to 3 times square root c plus 1. So from what we substitute with 3, we got 16 over 3 minus when we substitute the number of 0, we got 2 over 3 equals to 3 times square root c plus 1. So 16 over 3 minus 2 over 3 equals to 14 over 3 equals to 3 square root c plus 1. And the 3 from the right, we transfer it to the left, which is it's going to be 14 over 3 divided by 3. It will be 14 over 9. So for the last step, we transfer the square root to the left. It will be square, which is 14 over 3 14 over 9 square, which is it will gonna be c plus 1 equals to 196 over 81. So lastly, for the A3, we can conclude that c equals to 1.19 in 0,3, which is 1 is between 0,3. So we can conclude that A3 equals to B1. For the condensed proof, to prove that fx equals to square root x plus 1 is continuous, we need to find a value c between the interval 0, 3 by mean value theorem for integral BA fx dx equals to fc b minus a. Then obtain from the integral, we substitute the number of 3 and 0, which is it will gonna be integral of 3, 0 fx, which is square root x plus 1 dx equals to square root c plus 1, 3 minus 0. Solving the integration, the value of c equals to 1.19 is derived, and this value is between 0 and 3.
So we're almost at the end, but before that, let's see what we can conclude overall. In conclusion, mathematical terminology provides a precise and universal language to describe mathematical concepts, ideas, and relationships. By applying it, we can better understand, explain, and discuss mathematical ideas such as terms like function and set. While construction method outlines systematic steps to solve problems or prove theorems by focusing on question of how to build a mathematical solution. By applying these methods, we can develop mathematical structures such as constructing proof and solving equations.